Hello viewers, welcome to today's lecture on transmission of digital signal. This is the second lecture on this topic. In this lecture, we shall cover these following topics. First, I shall give a brief introduction. This will be followed by scrambling coding schemes. Then we shall discuss basic concepts of block coding steps, conversion of analog data to digital signal. This will be a different type. Then two basic approaches of analog data to digital signal, that is pulse code modulation and delta modulation. Then we shall discuss limitations of pulse code modulation and delta modulation. Then compare these two approaches. And on completion of this lecture, the students will be able to explain scrambling coding schemes, explain the need for block coding, explain the cooperation of block coding. The students will be able to explain the coding techniques used for conversion of analog data to digital signal. They will be able to distinguish between the coding techniques such as PCM and DM, which are used for coding from analog data to digital signal, conversion of analog data to digital signal. Then they will be able to compare the advantages and limitations of pulse code modulation and delta modulation. Here is a summary of what we discussed in the last lecture. In the last lecture, we started our discussion of transmission of digital signal. Essentially, we discussed various schemes for conversion of digital data to digital signal. So here is a summary, and as you know, the conversion technique is known as line coding, and they can be classified into three broad categories: the unipolar, polar and bipolar. And unipolar, as you know, is not really used, but the polar scheme has a number of different types like NRZ, RZ, Manchester and differential Manchester. All of these coding techniques we have discussed in detail. We have also discussed one particular technique of bipolar encoding, that is your amplitude AMI, amplitude mark inversion, that we have discussed in detail in the last lecture. Let us pick up where we left in the last lecture. I mentioned that although AMI is a good scheme, it has some limitation because it does not provide you synchronization. Although it is very good from the viewpoint of bandwidth, it does not have a large bandwidth. Bandwidth is not high, and that is why it is attractive from the bandwidth point of view, but it does not provide good synchronization. So how this problem can be overcome, retaining the advantage or good feature of bandwidth? That is what is being tried in B8ZS, which stands for bipolar with A80 substitution. As I mentioned, the limitation of bipolar AMI is overcome in B8ZS, and which is particularly used in North America. As you have seen, the main limitation of amplitude mark inversion was that whenever you have a long sequence of zeros, there is lack of synchronization. Synchronization fails because there is no signal transition whenever you have a long sequence of zeros. How that can be overcome, that we shall discuss today. What is done in this particular case, whenever you have got 8 zeros, that is being replaced by the following encoding. Whenever the sequence of 8 zeros, whenever you have a sequence of 8 zeros, it is replaced by 0 0 0 plus minus 0 plus minus if the previous pulse was positive. On the other hand, if the previous pulse was negative, then that sequence of 8 zeros is replaced by 0 0 0 minus plus minus 0 plus and minus. So you see the zeros, the normally it should be 8 zeros. So, in place of 8 zeros, we are the sum of the zeros are being replaced by positive pulse, negative pulse, 0, positive pulse and negative pulse. Now, this should be done at the transmitting end, and also it should be done at the receiving end, and that's only then it will be possible to do communication. So, it is some kind of protocol that is being followed by both sides for data communication. So, you see here, as long as the number of zeros does not exceed 8, then there is no problem. When it is 8 or more, then 8 zeros are replaced by this code. Let me illustrate it with the help of an example. Suppose the bit sequence is 0 0 0 1 1 0 0 0 0 0 0 0 0. Here you have got 8 zeros, 1 2 3 4 5 6 7 8, and after that it has got 1 0 0 0 0. There are 4 zeros. After that there is a 1 1 0 0. So, if we use bipolar AMI, as we find there is a transition from 0 to 1 here, and another one is there. So, again transition from +1 to -1. So, as we know, the bipolar AMI uses 3 levels: 0 level, positive plus B and minus B, positive and negative. And for each occurrence of 1, as we know, there is inversion of the pulse. That means, for this one it is plus B, and for the next one it is minus B. And as you see here, as long as there is no 1, here all are 0. So, there is no transition, only whenever there is a 1 here at this point, then again there is a opposite transition. Here it was negative transition, here it is a positive transition. Now, these 8 zeros are replaced by 0 0 0, and here V stands for bipolar violation. Why we are introducing violation? You may be asking, why violation? The reason for that is the other side should be able to understand that this is not a proper code. So, it has been forcibly introduced for the purpose of synchronization. So, it will be replaced by all zeros. That means, here as you can see, these two will remain, then 0 0, after 0 0 0 there will be a violation, then the next one is B, then 0 positive, then again violation. You see here there are 2 violations, and then opposite one minus B. So, in this case, since it is followed by a negative transition, as we have seen in the previous case, if the previous pulse was negative, then it will be 0 0 0 negative positive 0 positive negative. That is precisely what is being done. 0 0 0 negative positive 0 positive and negative. So, that has been done in this particular case, and as you can see here, now we have enough transitions, so that at the other end the receiver will be able to regenerate clock and synchronization will be achieved. However, in this particular case, as you can see, there are 4 zeros, 0 0 0 0. These zeros, however, is not replaced, but as I said, as long as the number of 0 does not exceed 8, no replacement is done. So, this is how B8ZS is code is sent, and this is being sent over the line. At the other end, this will be received, and this will help you to achieve synchronization, and then you will be able to get back your original signal like 0 1 1 0 0 0, whatever it was, that can be retrieved, and from these violations you will know that this has been introduced, so that enough transitions are there, but these are not really the transitions related to that bipolar AMI code. So, this is how the B8ZS works. Now, the another alternative code is the high density bipolar 3 zeros, and in this case of this particular alternative is used in Europe. The previous one was used in America. This is particularly used in Europe and Japan. So, it replaces a sequence of 4 zeros by a code as per the rule given in the table below, not above, but below. So, here as you can see, it also depends on the polarity of the previous pulse. If it was negative, then it is replaced by 0 0 0, and if the number of bipolar pulses since substitution is odd, then it is replaced by 0 0 0 negative. On the other hand, if the number of substitutions was even, then it is replaced by positive 0 0 0 positive. Why, you may be asking why this is being done? This is done so that the average value is 0. That is the purpose. Similarly, if the polarity of the preceding pulse was positive, and if the number of bipolar pulses since last substitution was odd, then it will be replaced by 0 0 0 positive, and if it was even, it will be replaced by negative 0 0 negative. Let me illustrate this with the help of an example. The same example is shown here. Here, as you can see, the number of substitutions was 2 and the previous pulse was negative. So, since the number of substitutions that have already taken place is 2, that means even, and the previous pulse is negative. So, it shows that it is even and number of pulse is negative. So, it is replaced by positive 0 0 positive. So, you see here it is positive 0 0 positive. Now, here again another 4 zeros are there. So, in this case, since the previous pulse is positive, here this will be done as per this rule, negative 0 0 negative. So, here you see negative 0 0 negative. So, this is how the 8 zeros, the first 4 zero is replaced by this code and next 4 zeros are replaced by this code, and you see here 2 positive and 2 negative. So, average value will be 0. Similarly, here again 0 0 0 0, there are 4 zeros. So far there are 1 2 and 3 ones. So, number of ones has occurred odd and the previous pulse is positive. So, in this particular case the rule followed is odd and it was positive. So, 0 0 0 positive. So, you see here it is 0 0 0 positive. So, here we get 0 0 0 0 positive. So, you see here also the violations are introduced. As we know, as per bipolar AMI code, it will next pulse has to be positive. So, but it is not done here. So, forcibly by violations are introduced, so that they are identified as signals sent for synchronization, and so that the proper data is retrieved from the received signal, and at the same time synchronization is achieved. So, here is the summary of the characteristics of B8ZS and HDB3. As you have seen, it uses 3 levels: positive, 0 and negative, and there is no DC component, which is a very good parameter or very good feature, and it allows good synchronization both the codes. And advantage is most of the energy is concentrated around a frequency equal to half the data rate. So, the bandwidth is less, and it is well suited for high data rate transmission over long distances. Let us look at the frequency spectrum. Here, as you can see, the compared to other codes we have already discussed, here is the B8ZS and 8GB3. Here is a nice spectrum that you have got, and most of the energy is centered around the middle of the bandwidth. So, here 1 corresponds to the bandwidth. So, most of the energy is concentrated in the middle of the bandwidth, which is definitely a very good feature, and that way it will allow transmission through a medium with lesser distortion and attenuation, because it will match perfectly with the most of the band pass nature of transmission media. So, we have completed all these codes. Now, there is another type of coding known as block coding. This block coding was introduced to improve the performance of line coding. So far, we have discussed various types of line coding, which is used for conversion of digital signal, digital data to digital signal for sending through the transmission media. But before you do the line coding, a technique known as block coding was introduced, so that the performance of line coding can be improved. Performance in terms of what? performance in terms of synchronization, performance in terms of bandwidth, performance in terms of error detections. These are the three important parameters which are considered. As I mentioned, it introduces, and the basic concept that is being used here is redundancy. So, it introduces redundancy to achieve synchronization. Also, because of the redundancy introduced here, it allows error detection, and apart from synchronization, it also allows error detection to some extent. Let us see the basic scheme used. Basic scheme has got three distinct steps. Division, for example, here is your input data. So, the division is MB division. That means, this sequence is divided in blocks of M bits. For example, if we are using say 4B, 5B encoding, in that case these M bits will be 4. For example, if the code is, if the input is, data is say 0 1 1 0 0 1 0 0 1, then it will be divided into say 0 1 1 0, this is one block, then 0 1 0 0 another block. So, this is how it is divided. So, it is divided in terms of M bits. Then that M bit is applied to MB to NB substitution. So, each M bit is replaced by N bits. So, in this case each of these 4 bits will be replaced by 5 bits for this particular example. Then ultimately these N bits are line coded, and a line coding we have already discussed, and that that output signal is transmitted through the transmission media. This is the basic scheme, and as an example, as I already mentioned, 4B 5 encoding. And while doing the encoding, here you see the encoding is done little cleverly. The 5-bit code is done in such a way that it has got no more than one leading 0 and no more than 2 trailing zeros. So, it is ensured that transitions are there, then more than 3 consecutive zeros do not occur. So, these are the two things are done, and finally, the line coding is done by using NRZ code. So, what you are essentially doing, suppose here it is the code set for 4B codes, and 4B codes, as you know, there will be 2 to the power 4 symbols, and obviously the 5B codes will be larger. So, here the 5B codes will have 2 to the power 5, that means here it is 16 and here it is 32. So, what will be done, these 4B codes will be mapped to a subset. So, it is mapped to a subset such that these properties are satisfied. That means 5-bit code has no more than one leading 0 and no more than 2 trailing zeros, and more than 3 consecutive zeros do not occur. This is how it is being done. You may be asking how error detection is done. So, you see, this is a code, this is also code, but here it is 5-bit code. Now, suppose after receiving at the receiving end, the code is not within this code. So, it becomes a non-code. So, when it becomes a non-code, then we know that some error has occurred during transmission from this side to the, from the transmitter side to the receiver side. So, that is how the error detection is possible in this case. Let us see the example, how the encoding is done. You see here there were 4 zeros, 4 zeros have been replaced by 1 1 1 1 0. This is 5-bit, this is 4-bit. 0 0 0 1 is replaced by 0 1 1 0 1 0 0 1, and you can see here you have got, when long sequence of zeros like 4 zeros or 4 ones, there are 0 and 1s are introduced, and as I mentioned, it was necessary to have no more than one leading 0 and no more than 2 trailing 0, that is being satisfied here. No more than one leading 0, you see, we do not find more than one leading 0, and no more than 2 trailing zeros. Here there are 2 trailing zeros, but you will not find 3 trailing zeros anywhere. So, this is how the encoding is done. However, you have got some other codes which are used for other purposes like quiet, idle, halt, essentially control codes. But so far as the data codes are concerned, it satisfies that synchronization property and it helps you to achieve error detection. Now, other block coding examples are 8B to 10B. So, here you have got 8-bit data codes, data blocks, and which are substituted by 10-bit code. So, each 8-bit data is encoded by 10-bit data. So, obviously, it allows you more redundancy, more redundancy. And obviously, more redundancy means it provides more error detection capability, but unfortunately, it leads to increase in bandwidth. Whenever you have got more redundancy, there is more error detection capability. So, unfortunately, this error detection capability is advantageous, but increase in bandwidth is not advantageous. So, this is acceptable, this is not acceptable. How do you overcome this problem? This problem can be overcome by using suitable line coding. For example, here we are using, say, let us assume that 6B to 8B encoding is done. So, 8B to, then the line coding can be done from 8B to 6T. So, suppose the after encoding the 8-bit data is 3F, 3F means this is 0 0 1 1, F is 1 1 1 1. Now, the while doing the encoding you are not generating 8 bits, but you are generating 6 values, 6 values for transmission. So, negative, 0, positive, negative, 0, then positive. So, this is, you see, you are generating 6 symbols for during transmission. Obviously, the bandwidth of this will be lesser compared to 8-bit signals. So, here is the advantage of this line coding. It reduces the bandwidth, but at the same time it provides you higher redundancy, higher error detection capability, and also synchronization. So, here we now change gear from digital data to digital signal to analog data to digital signal. There are many situations where we have to send analog data, but we want to send in digital form or we want to send in the form of digital signal, because sending that signal in the digital form has many advantages from the viewpoint of signal to noise ratio and other things. For example, analog data such as voice, video and music are to be converted into digital signal for communication through transmission media. One example is, say, voice that is being sent through telephone line. So, here we are trying to send analog data, but as you know, in modern telephony it is not sent in analog form, it is converted into digital form. So, digital signal is transmitted. Similarly, video and voice, video and music can be sent. And for that purpose, there are two basic approaches. The two basic approaches are, first one is known as pulse code modulation and second one is known as delta modulation. So, in this lecture today we shall discuss about these two schemes, pulse code modulation and delta modulation, one after the other. Let us first concentrate on pulse code modulation. The pulse code modulation has got three basic steps: sampling, quantization and line coding. Suppose this is the analog signal. So, this analog signal has to be converted into digital form for sending through a transmission media. First step is known as quantization, or first step is known as sampling. The sampling process converts the analog data, analog signal, you can say this is essentially analog signal into a form known as pulse amplitude modulation. So, PAM stands for pulse amplitude modulation. How it is done? This analog signal is sampled at regular intervals. Say this is the interval. This is the interval at which it has to be sampled. Obviously, they will be equispaced. And when you do the sampling, as you know, you have to follow the Nyquist criteria. Nyquist criteria says if the signal has a bandwidth b, then the sample rate has to be 2b. Suppose you are sending voice signal. The voice signal has a bandwidth of 4 kilohertz. So, your sample rate has to be 8 kilohertz. So, that is the rate here in this direction it is being sampled. Now, the sampling is done here, 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 here at these points. So, as you sample it, now you are also holding that value till the till the next sample. Then you are again increasing, then you are holding it to the next sample. Then you are going to the next sample, again holding it for till the next sample. Then you are going there, holding it to the next sample, and then you are holding it to the next sample, the next sample value. This sample value again you are holding it to the next sample value. Here again you are holding it to the next sample value. Then again you are sampling it, holding it to the next sample value. In this way, you convert it into a signal, and this signal is known as PAM. That means, this signal as we have obtained after sampling it and then holding it for the next duration, this with the help of a hardware known as sample and hold circuit. Sample and hold circuit will be able to do this. And this signal that is being generated at the output of the sample and hold circuit is known as PAM. Now, this PAM has got different values. So, you have to now do the quantization. Quantization is done with the help of a hardware known as analog to digital converter, AD converter. AD converter will do the quantization, because that analog to digital conversion is done, and the analog to digital converter will have limited number of bits, say 8 bit or 6 bit. If it is 8 bit, then it will have 256 different quantization levels. So, now the analog value was having all possible voltage levels. It is now converted into some discrete values depending on the number of bits used in the analog to digital converter, and that leads to what is known as quantization error, as we shall discuss later. And after we have got the digital data, it can be done converted into digital signal using suitable line coding, which we have already discussed. So, this is the process. Analog input signal, which is obtained maybe from microphone, with the help of a microphone. If it is voice, then using sample and hold you are converting into PAM signal. Then AD converter has got two parts, quantizer and encoder. Then it generates the digital output as it is shown here. So, this is the analog signal, this is the sample pulses, and this is the PAM signal, and after quantization and encoding you get the binary output, the digital data that you are getting, which can be line encoded for sending through the transmission media. So, this is the transmitter part, which generates digital output signal from the analog input signal, and then this digital input signal can be transmitted through the transmission media after line coding, which will be received at the receiver, and again you have to perform the reverse process. The reverse process first is done with the help of digital to analog converter or DA converter, and the DA converter will generate analog signal which has to be filtered. You see, earlier we have, after PAM we got the quantized values, that has to be smoothed with the help of analog, with the help of filter, and we shall get the analog signal recovered from the system. So, this is your receiver and here is your transmitter. This side is your transmitter. So, these two sides, this side is the transmitter and this side is receiver, as I have shown. As an example, let us consider an input signal which is voice, which has a bandwidth of 4 kilohertz. As I said, the sampling frequency has to be at least twice the highest frequency in the input signal, otherwise a problem known as aliasing error will occur. You may be asking why the sampling rate has to be more than twice this the maximum signal. If if it is not done that way, it will lead to a kind of error known as aliasing error. We shall not discuss it further in this lecture. So, you have to, sometimes the signal is band limited before doing the sampling to avoid aliasing error. So, the 4 kilohertz bandwidth signal is sampled at the rate of 8 kilohertz, and then you are using an analog to digital converter and the using an 8-bit AD converter, that means each sample value is converted into 8-bit. So, each sample value, that means you have got in 1 second 8k sample values and you multiply with 8-bit to generate a digital data having 60 kilobits per second rate. So, data rate is 64 kilobits per second. So, you see here a voice of 4 kilohertz bandwidth, whenever you convert into digital data, has got a 64 kilohertz kilobits per second data rate. This is the data rate, and this has to be properly encoded by line coding and then send over the transmission media. As I mentioned, whenever you use a sample and hold, use an analog to digital converter of suitable number of bits and quantization error is introduced. Essentially, it depends on the step size. Suppose you are using 5 volt, that means maximum it is from say 0 volt to 5 volt, and quantization level is 8 bit, that means 256 levels. So, the step size is essentially 5 volt by 256. So, any intermediate levels between this 5 volt by 256 will be translated into those discrete values, and that will lead to error. And this uniform, and also what we are doing, even when the input signal is of low amplitude or high amplitude, we are encoding by using the same step size. We are not doing conversion in a different way. As a result, with the constraint of a fixed number of levels, the situation can be improved using variable step size. Because of the fixed step size, the signal to noise ratio is more for high level signals. Unfortunately, for small amplitude signals, the signal to noise ratio is poorer. How that can be overcome? That can be overcome or improved by using variable step size by a technique known as compounding. It is essentially a technique by which we are introducing nonlinear encoding. That means, whenever the signal amplitude level is low, then we are using little higher step size and smaller step size, so that we get the better accuracy. On the other hand, when the amplitude level is high, step size can be higher. So, that is precisely what is being done in this case. For that purpose, what can be seen, we can use a nonlinear circuit to convert the signal in this form. So, here as you see, for low amplitude values here, this particular curve, you see whenever you are not using compression, it is linear for all values, smaller values and higher values. The rate of, that means for rate of change, the slope of this curve is same in this particular case. But whenever you are using compression, then you see this slope is more than whenever you have got higher values. That means slope is more for smaller values than higher values. Then after passing through this nonlinear circuit, the you can apply the signal to the analog to digital converter, and this will avoid the problem that we have already discussed. So, what we are doing, the steps are close together at low signal amplitude and further apart at high signal amplitude, and this improves the signal to noise ratio, particularly when the signal level is low. So, a compounding is a technique which can be used to improve the signal to noise ratio. Now, let us look at the limitations of pulse code modulation technique that we have already discussed. Pulse code modulated signal has got high bandwidth, as we have seen. Say 4 kilohertz analog signal will require a bandwidth of 4 kilobits per second. As you have seen, a voice signal you require a data rate of 56 if you are using 7-bit encoding, or 64 kilobits per second if you are using 8-bit encoding. To overcome this problem, a technique known as differential PCM can be used. So, in differential PCM, as you can see, can be used whenever you have got whenever you are using this PCM technique. But this is based on the observation that whenever you are using PCM, I mean sending analog signal, we have observed that the signal is changing very slowly. Since the voice signal changes very slowly, why not send the change rather than the absolute values? That is the basic idea of this the differential PCM. So, you see, so instead of sending the absolute values, the difference between two consecutive sample values instead of the sample values may be sent. This is the basic idea of differential PCM. Since the signals are changing slowly, the difference will have small values. So, the number of bits required will be less. So, bandwidth will be less. So, that is the basic idea of this differential PCM. And you can use either analog technique or mixture of analog and digital technique, or purely digital technique to do this. We are not discussing the details of it, but it can be done in one of the three ways to generate differential PCM signals. However, a very special case of differential PCM is DM, which stands for delta modulation. In what way it is a special case of differential PCM? In differential PCM, what we are trying to do, we are sending the difference between two consecutive sample values. Now, what we are doing, the difference we are reducing to a single bit. We are sending either 0 or 1. That means, if the difference is positive, that means if the next sample value is more than the previous sample value, we shall be sending 1, and if the previous sample value is more than the present sample value, then we shall be sending 0. So, instead of sending 8 bit per sample, we shall now send only 1 bit per sample. That is the basic idea of delta modulation. So, depending on higher or lower, we are sending output 1 or 0, and we are sending 1 bit at a time. As a consequence, the bandwidth will be much less. As you can see here. So, this is the example of delta modulation. So, here is the analog signal changing very slowly, as you can see, and this change is being monitored, and you can see here if it is increasing, that means the previous sample value is more than the previous sample value is less than the previous sample value, you are sending ones, and whenever it is less, we are sending zeros. So, we are sending 1 bit at a time.
So, the bit stream that you have to send is 10 10 10 111 and so on, and you can see here per sample we are sending only one bit. So, the bandwidth is less as you can see in case of delta modulation, and you can use a circuit like this, a analog comparator. Here is the analog input, and with the help of this clock we are finding out the whether this comparator output is 0 or 1, and depending on that you are sending 1 or 0, and with the help of that this is essentially some kind of integrator or adder which regenerates the reconstructed signal. That means analog waveform that you are receiving is reconstructed here, and with 1 bit unit delay you are feeding it, so that the previous value is compared with the present value. Here is the previous value and here is the present value. These two are compared with the help of this comparator. And with the help of such simple circuit you can generate the delta modulated signal. Here you get the zeros and ones, the binary output and which can be sent to the transmission media after suitable line coding. The receiver also here you can see is very simple. Here is a simple adder. The previous value after 1 bit delay is added with the binary input, and then the reconstructed waveform is obtained here. So, we can see here delta modulation does not require complex hardware. So, here are the advantages of delta modulation. Simplicity of implementation. Each sample is represented by a single binary digit as we have seen, which makes it more efficient than pulse code modulation technique. However, there are two important parameters: the step size, the size of the step, and the sampling rate. These two plays a very important role. In what way? Let us see in the next slide. This fixed step size leads to overloading. What do you mean by overloading? As you can see here, if the signal analog signal is changing very slowly, we can see the data that you have to send will change, will become 0 1 0 1 alternately it has to be sent. This leads to overloading. That means slowly changing. If the height step size is such, if the input changes within the step size, then alternately you have to make 0 1 0 1. This is known as overloading. And overloading occurs not only due to higher voltage, but also due to slope. Higher loading, that means whenever it exceeds the limit, then it is overloading. Whenever moreover error arises whenever the slope is fast, then we call it slope overloaded. As you can see